Okay, so now we have this intuition that the constraint, like with the constraint model, we can be better off, right? And then we have this parameter C that helps us in controlling a more complex model, especially when dealing with noise. So we are going to build upon that, and especially using a linear model. So just imagine we are in this transformed space already, the Z space that we talked about some time earlier, and the weights in the Z space were denoted by W tilde, but I'm just getting rid of this W tilde so that I can get a more cleaner notation and avoid any confusion. So here, basically what I'm saying is my hypothesis set is nothing but W transpose Z. Notice the W's are referring to the W tilde, but I got rid of that, such that my W transpose W is less than this constraining parameter that we talked about earlier, right? And so we already discussed a lot about this, so I'm not going into the details of that, but rather what we are interested in is that we want E in of W, the error term, to be minimized, right? And just a quick reminder, this was the error term in our linear model, and we took some time, I remember, deriving that, so let's not repeat that. So here we have. Now, without the constraint that we have here, this one, right? Without that constraint, this original problem for a linear model without the constraint had a solution, right? And we found that solution using the pseudo-inverse algorithm, and the weights are denoted by W lin. So that was given by pseudo-inverse Z times Y, and if this was invertible, then Z transpose Z inverse Z transpose Y. We already know this result for a linear model for an unconstrained model, the original one, right? But now we have a constrained minimization problem, and let me kind of like define this thing. So basically what I'm trying to say is that I want to minimize this E in of W, right? Over all the weights, of course, subject to this constraint. Right? This is what I want now. So in general, this problem is difficult to solve, but in our case, it's manageable because we have this linear model, which is easier to manipulate, first thing. And then the second thing is that my E in here is a nice convex function. And you know that these convex functions have certain mathematical properties that help in optimization. Okay, so let's see what we are trying to optimize and how should we optimize that. And let me move to the next slide. Okay, so there could be like many scenarios. So the first scenario that I'm looking at is like maybe a nice case, right? So maybe I can have this W lin, the one that I'll get in the unconstrained optimization is such that this is the case, like it does not violate my constraint, right? So if it does not violate my constraint, then there is nothing left to do because my W, and by the way, the regularized weights will be denoted by WREG. So essentially, this is my regularized weight. I got the optimal value. So if the like unconstrained version works well, I don't need to do anything and we are done. But that is rarely the case. In 99% of the situation, and this is like case 1, case 2 happens. 99, more than that, like 100% of the time, I would say. So what happens is W lin transpose W lin is most of the times greater than C. Okay, so what does this look like geometrically? Because this problem is easier to understand if we look at the geometric interpretation of this. So this part is essentially like a sphere in whatever dimension we are working with. So if it's a 2 dimension, it's a circle, right? And so this is like the feasible set. So the feasible weights should that satisfy our budget constraint. And this, by the way, is our budget constraint. This thing here, this is also known as the budget constraint. So I'll talk more about that, but let's look at this. Now this thing essentially tells us that this is my feasible set. This is what I'm looking at when I'm constraining it. So this is my feasible set, correct? And what that means is the radius. So this is nothing but a sphere. Like this is in a 2 dimension, it's an equation of a circle, right? And so the radius of this would be square root of C, right? So this is the geometric interpretation. Now we have something that's W lin, which we would have which would have resulted when we solve the unconstrained problem, right? And because this thing, like we know that this is true, so maybe WLin lies somewhere here outside the feasible set, right? So what's going on in there? Now, because this is my unconstrained WLin here, WLin, okay, let me make it like that. Let's say we have that point there. So let me just get rid of that. And let's add this here. So let's say this is my WLin. This is a better one. And linear or lin, not linear, right? And so this is my unconstrained WLin that will minimize my error. So that means my E in is minimized at this point. So this tells me that as I move away from this point, E in will begin to grow, right? And so what does that mean? Now E in is convex. So let me write these things down here. E in is convex, and in fact, it's so good that it's like almost quadratic in our like this case, this problem. So this is quadratic, which means that like the geometry of my E in is like more like a contour, right? So like these elliptical, I don't know what to call them. So these are the contours, well-defined contours that like represent E in, which means that every contour that we can build like this has like a constant, I would say, a constant E in on each of these, like this surface, right? Because this is like a quadratic or an elliptical kind of a contour, and every point on this has a constant E in because this is representing an E in some space, right? And as you move away from this WLin, which was my optimal result, which minimized my E in, right? My E in will increase. So with every contour, E in is increasing. Now, we're using a result from calculus, which is telling us that the gradient on a contour, like along the contour, is, if, for example, if I move the weights on the surface of the contour, there is no change in error. So therefore, the gradient of the error along the contour is 0. And what is the gradient of the error? Normal to this, and gradient of E in is 0 along the surface, right? So the gradient on any contour, which is the surface of constant error, is 0, and that this gradient is normal to the contour of constant E in, which is what we can see here. Now, I can choose any weights that are as close. What is my goal? My goal is to get a weight that has like a small E in, like as small as possible, but then it has to lie within this like feasible set as well, right? So basically, I'm looking for feasible weights that satisfy my constraint, right? And also have a small E in. So I'm trying to have weights that are as close as possible to the linear fit, like to one of these contours. So the optimal solution has to lie, if you think about it, the optimal solution has to lie on the surface of this, because like if I, for example, say this is the weight that I'm looking at, then of course you can move a little bit down to improve, right? Or if I'm selecting something here, then you can move along the surface to improve. And so the best solution, which is feasible as well and also has the minimum E in, would lie somewhere like this, is what I'm trying to say, right? So basically what I'm saying is one possible solution could be this, like, and let's denote it by a star. Now, like if inequality constraint becomes equality constraint at this point, then we can use a method that's known as the method of Lagrange's multiplier to solve this problem, right? First, let's look at the geometric interpretation of this in more of a like a more detailed way. So which basically, again, if this is the point, right? And if I move towards the top, that means if I keep moving on the surface and keep moving above, right? Then I'm moving towards a contour of a higher error. Similarly, if I move down from this point, again, I'm moving towards some other contour here, which has a higher error, which is away from this WLin, right? And so basically I have to like continue to move until I find that contour that is tangent to the surface. So that's exactly what I'm trying to tell here, correct? So the optimal has to be a point on the constrained surface that is tangent to a contour of constant E in, because that's the best that I can do. Okay, so let's look at it in a better sort of way. This is my E in. This is what I'm trying to minimize subject to the constraint this, right? some of the observations here are that, like, let's say E in is constant on this contour. And so if this is like some random contour and I chose my W to be this one, right? So I can definitely get better if I move up here somewhere, right? Because I want to be as close as possible to W lin, right? I want to be as close as possible to my W lin and then also like not violate my constraint, right? So if we are at optimal point, then the gradient of the in-sample error, right? And that's what we are like showing here. So basically the first observation is optimal W tries to get as close to W lin as possible. Why? Because of this equation, right? We know that. Now the surface at optimal W would be perpendicular or would be normal to my E in somewhere here. So this is going to be the gradient of E in, and my whatever weight here would be in the opposite direction, right? And so what is this trying to tell us? This is trying to tell us that the normal to the sphere, which is like my W vector right here, is in the direction of the weights, and that is in a completely opposite direction to this delta, to this gradient of E in. So basically what I'm trying to say here is that at that optimal point, the main observation is that the gradient of my E in, whatever that E in contour would be there, right, is directly proportional to the negative of the weight vector, of that optimal weight vector. And this is an important and very necessary condition for optimality. And we can say that here geometrically, and although this can be proven analytically as well, but here we are saying that geometrically, and we can see the intuition behind it, is that the gradient of my error term has to be directly proportional to the negative of the weights. Okay, this is the necessary condition for optimality. So let's write that down. This is a necessary condition for optimality, and we can see that geometrically why that is the case. So basically what I'm trying to establish is that the gradient of E in is directly proportional to, as I said, the negative, the weights or the weight vector, or like we can, instead of this like directly proportional, we can change that with an equality sign such that I introduce a constant here, right? So what I'm going to do is I'm going to introduce a constant along with this number 2. So negative stays. I'm coming to why this number 2 is included. But first of all, let's focus on the constant and W. So this constant is nothing but like Lagrange's multiplier and is always a positive value. This is also known as Lagrange's, and I think many of you would be familiar with that from your, I think, optimization classes. Multiplier, and is a positive value always. You can see, like, in addition to that, there is a C that I'm making use of, and this is referring to the C that we talked about earlier, the budget that we allocate to our problem, and so we'll talk more about it, but this lambda is in a way a function of that budget. So this is the necessary condition for optimality, and this 2 has been added for mathematical convenience, and this will become clear in a minute why. Okay. So because this is a necessary condition for optimality, we have established that. So let's rewrite it. Let's rearrange a little bit of the terms. The gradient of E in plus 2 lambda C W should be 0, right? This is when optimality will happen. If you really look at this this second term, this is nothing but the gradient of this term. This is the gradient of, just think about it, it's the gradient of this constant, whatever it is, W transpose W, right? If we calculate the gradient of that, this is what we are going to get. So we can say that this is also equivalent to writing the gradient of E in, right, plus lambda C W transpose W equals 0, right? So now we are trying to basically say that the gradient of this term should be equal to 0, and that is the necessary condition for optimality. So basically, if the gradient of this is 0, then this term is minimized, right? So basically, we have come down to solving the problem of minimize E in of W plus lambda C W transpose W, because this was my condition for optimality. And how do I achieve this condition when I'm saying that I'm trying to minimize this? So I'm going to obviously calculate the gradient and set it equal to 0, right? And so what have we achieved by doing all of this, right? Why did we do all this manipulation and whatever interpretation through geometry and all? Well, we did that because earlier we had a constrained optimization problem, constrained optimization, and we are now able to reduce it to an unconstrained optimization problem. As you can see, there is no constraint in this problem. Right, and let me show you what the original problem was. So this was our original problem, and now we have come down to this nice unconstrained optimization problem, which is more convenient when we try to solve it. Okay, so let's look at a few of these things here. So for example, we have this lambda c. Now lambda is a function of c, as we said when we defined it, right? So basically it's a function in a way that if lambda c goes up, lambda c increases, right? And then c must go down. So they are related in that sense. So c must go down, which means I should have a lower budget. So this is kind of telling me that this is like a parameter that helps me control in some ways C, because C is the budget that we choose. And although there is no direct way of interpreting the exact value of lambda C, but we can think of it as a penalty that we pay depending on the size of the weights. Because let's say the weights are really, really huge, and so you have to accommodate the like within the budget, and so you will make the lambda go down, right? So you have like so basically what you have to do is you have to have a higher penalty for that, right? So equivalently, our problem is unconstrained penalized problem with the parameter lambda c. That's what we are trying to say here, right? And again, I'm repeating, lambda c is considered as a penalty that we pay depending on the size of my weights. Okay, so having said that, let's kind of put everything together. In conclusion, what do we have after all this derivation that we did just now? So in conclusion, initially what we had was a problem that was fitting under a constraint, or a budget, right? Something that we decide. And now we have something that's known as an unconstrained, penalized. It's because we have a penalty now, right? Penalized fitting problem, or fitting with penalty parameter lambda. So we have a parameter for that, which is lambda. Okay, now putting it more formally, what we are trying to do is we are trying to minimize E augmented. Now this is a new definition. Basically what we are trying to do is we are trying to put these two terms together and like and just like saying that this is like E augmented, because like you have this penalty term attached to your E in, right? So basically I'm trying to minimize the E augmented W, which is nothing but E in of W plus lambda C W transpose W. And also like to make things cleaner now, instead of like explicitly writing C all the time, I'm going to get rid of the C. Okay, so now we have this augmented error, and all we are trying to do is that we are trying to minimize this. So now we are not just minimizing E in, but we are minimizing this augmented error that has this penalty term here attached to it. And notice that we've introduced this N here, right? And this is for practical considerations. For example, if N is large, penalize less. And so lambda is more stable across different data sets. And that's why we have introduced this like the size of the data set as well in this equation. Okay, so the like what we are trying to like, let's rewrite this. So we are trying to minimize the augmented error, which is nothing but E in of W plus this lambda over N and some omega, which is a function of W. Okay, So we call this the penalty term. This is the penalty term in my augmented error. It's a function of W, so we are penalizing the complexity of the hypotheses, right? So what are we penalizing? The complexity of my hypotheses. Complexity of hypotheses. For example, if we chose, let's say, if there was a polynomial of some higher degree, then we have weights according to that. So we have to penalize the weights according to that. So we can further write this as, this is the augmented error, which is for that hypothesis that we are trying to eventually implement. And this is a function of the complexity of my hypotheses. So basically that's how this augmented error is expressed. Or maybe we can say that these are two equivalent to one another. A little bit of notation here. This term here, W transpose W. So this is defined as the regularizer. So whenever we come across this means this is the regularizer, and we get to pick this. We pick this as like an input parameter for our problem. Similarly, we have lambda, and this is known as the regularization parameter. Regularization parameter. Okay, so again, we get to pick this. There are some known standard regularizers, and the recommendation overall is to pick some standard one because they have certain properties that are more beneficial for us. And so there's a lot going on here. There can be different types of regularizers. In terms of the regularization parameter, that's lambda, it's like a knob. Think of this as a knob that turns the complexity of the final hypotheses up or down, right? So this can be like thought of as a knob that controls the complexity of my final hypotheses. And this idea itself resonates with the VC theory, right? If you remember, my E out used to be less than equal to E in plus some function of the complexity of the hypotheses, right? And the only thing that has changed is that we have this like penalty term here. So we have a knob to control the complexity now. Earlier, we just knew that the complexity is there, and then we were doing the different things with the hypothesis sets itself, but now we have a way to control it. And so this resonates well with the VC theory. Now, in the next video, let's look at an algorithm that works with the linear models and how regularization happens in there.